Dear colleagues, I'm Peter Lohmander from Sweden. Thank you for inviting me to this conference. Today I will give you a presentation of optimal dynamic forest fire management adapted to stochastic weather. We will also get the presentation of the empirical data and background from my colleague Dr. Zohreh Mohammadi from Czech University of Life Sciences in Prague. This presentation is based on the following open access articles and documents. More details can be obtained from the links found below. I suggest that you read the abstract at a later point in time. This presentation is divided into different parts. First, we look at the firefighting capacity optimization problem in general terms. Then we look at the general solution to the firefighting capacity optimization problem. We will look at comparative statics analysis of the optimal solution. How is the optimal solution affected by the parameters? We will then go to fire growth as a function of weather conditions. We will also investigate background to the empirical weather and fire data. We'll go to dynamic and stochastic properties of air temperature, relative humidity and wind speed, and finally end with some conclusions. This page shows the firefighting capacity optimization problem. Forest fires have a spatially uniform probability density function. Firefighting units marked with blue balls have initial locations in a regular infinite network with roads in directions north to south and east to west. The distances between roads is small, and firefighting units can always use roads in the two directions to reach the different fires. See the purple arrows. The decision problem is to determine the optimal value of k, where the distance between the nearest neighbors is L, which is 2k. The optimal value of k is affected by many different parameters, some of which are functions of the season, for instance air temperature, relative humidity and wind speed. These parameters affect fire growth. We are interested to minimize the expected total costs as a function of k. Firefighting groups are located in a regular network with roads in directions south-north and east-west. The distance in one of these directions between two neighbor groups is L, which is 2k. So k is a decision variable. Ci is the expected cost of firefighting capacity investment and use of these resources. And Cf is the expected cost of destroyed and damaged forests, including costs of CO2 emissions. In this picture we see Cf, the expected cost of destroyed and damaged forests, and see how this is containing different parts, namely the expected cost per burned hectare, CD, the expected number of fires per time unit, capital N, and B, the expected size of burned forest per fire, where B is a function of air temperature, humidity, wind speed, and the time that the fire has been alive, where this is a function of K, and M, where M is the fire lifetime before the firefighting unit leaves the initial location and starts to move towards the fire. The expected cost of firefighting capacity and the use of these resources is the expected cost per unit times the number of units per 10,000 square kilometers. And you see the equation down where this can be transformed to a function of k. The expected size of burned forest per fire can be seen as a product of two components, namely b1 and b2, where b1 is a function of k and m, and b2 is a function of a, h, and w. Now b1 can be expressed as a function which you see in the bottom, a quadratic function of k and m. The curious observer may wonder why b1 is this particular quadratic function of k and m. And now we look at that in some detail. First, we consider x as the east-west coordinate and y as the south-north coordinate. And we remember that the probability density functions in both directions are uniform, and we see them to the right in the graph. Our interest here is to know how long it takes for the fire unit to reach the fire. Therefore, we have to know how far east and how far north the fire unit has to go to reach the fire when they start in the corner down to the left. And we denote the move in the east direction, x, and the move in the north direction, y, and z is the total distance. And the probability density function of z is shown at the bottom of the page. When we calculate the probability density function of the distance z, we get this result. And here we see that f, as a function of z, is a triangular function. The size of a fire area is generally proportional to the square of the time that the fire has been alive, if conditions are constant during the time of the fire. So, therefore, we see this expression z plus m in square used in the expression of b1. And also this is used in combination with the probability density function of z. So here we use this information to get b1. And of course we want to know exactly the value of b1. And in the following pages we'll see how we can get this as an explicit expression of the parameters. Now, finally, we know why b1 looks exactly like the quadratic function that we saw in the beginning of this presentation. And since this is a quadratic expression, we can easily take the first and second order derivatives, and we find them in the end of this page. And we also see that they are all strictly positive, which is very useful when we make the next derivations. Now we move to the general solution to the firefighting capacity optimization problem. Welcome! So this is the problem. We want to minimize C, the sum of Ci and Cf, and they are both functions of k. And we see the expression in two versions. One is more general than the other. In row 1 we have the minimization problem. In row 2 we have the first order optimum condition, and in row 3 we have the second order minimum condition. And we see that the second order minimum condition is always satisfied, which means that the first order optimum condition gives a unique minimum. In this page we see that dc dk intersects the k axis only in one place, and that's where we have k star, the optimal value of k. Now it's time for comparative statics analysis of the optimal solution. The question is, how is the optimal solution affected by the parameters? In comparative statics analysis, we look at the first order optimum condition, and we look at some change in some parameter. This change in some parameter affects the first order condition, which means that we have to change the optimal value of k star. And when we have the optimal adjustment, the first order condition is again satisfied. This way we can determine the derivative of the optimal decision k star with respect to the parameter. In these derivations we get the conclusion that if the cost per firefighting unit increases, the optimal distance between firefighting units increases. And this can also be seen graphically. In the same way, we can derive the following result. If the cost per fire-damaged hectare of forests increases, the optimal distance between firefighting units decreases. Note that if the cost of CO2 emissions is considered, the optimal value of k is lower than if we do not care about CO2 emissions. And this can also be seen graphically. If the expected number of fires per area unit increases, the optimal distance between firefighting units decreases. And if the general fire speed parameter c increases, the optimal distance between firefighting units decreases. Possible reasons: more open terrain and/or larger amounts of dry grass or other fuels. If the fires get more time to grow before the fire suppression starts, m increases, and the optimal distance between firefighting units decreases. Possible reasons: less efficient and/or intensive fire surveillance, fog, smoke or worse road conditions, forcing the firefighting units to decrease the travel speed. The comparative statics analysis now needs some empirical information, and therefore we will look at fire growth as a function of weather conditions. Relative humidity, air temperature and wind speed affect the size of a burned area according to the function found here. The publication where this is developed is found to the right, and there you also find the link where you can read more about this. In the graph you see that this function is highly nonlinear. The empirical estimations gave these results. We remember B2 as a function of air temperature, relative humidity and wind speed. And the derivative of B2 with respect to air temperature is strictly positive. The derivative of B2 with respect to relative humidity is strictly negative, and the derivative of B2 with respect to wind speed is strictly positive. Now we use the new empirical information and come to the following conclusion. If the air temperature increases, the speed of fire growth increases, and the optimal distance between firefighting units decreases. If the relative humidity increases, the speed of fire growth decreases, and the optimal distance between firefighting units increases. And finally, if the wind speed increases, the speed of fire growth increases and the optimal distance between firefighting units decreases. Comments on the optimization problem. Above, we have assumed that labor employment constraints are applied that require that the numbers of firefighting units at different points in time are determined before the true weather component residuals are known. Optimality conditions of the dynamically changing firefighting capacity levels have been analytically determined. The solutions have been found to be unique minima. Comparative statics analysis has been used to determine the directions of change of the optimal capacity levels under the influence of alternative parameter changes. The expected fire sizes can also be numerically approximated via random numbers with relevant correlations based on Cholesky factorization. A stochastic dynamic programming version of the dynamic investment decision problem is also possible to present based on a very flexible labor market, where the number of firefighting units rapidly can be adapted to the sequentially revealed weather situation. However, since time is limited and since such labor conditions are not relevant in many countries, this will not be presented here.
Hello, this is Zohreh Mohammadi. I'm a postdoc researcher at the Faculty of Forestry and Wood Sciences at the Czech University of Life Sciences in Prague. In the project, we are working on evaluating uncertainty techniques and risk assessment methods for providing decision support in the Czech Republic forests. Between 2006 and 2020, an average of 726 forest fires were recorded annually in the Czech Republic. The total burnt area across this year was 25.8 kilometers square, and the average was 2.58 kilometers square per year. The dominant type of forest fire was ground fire. The data included the date, location, area burnt, and the number of wildfires from the database of the Czech Republic Wildfire Rescue Service for the study period 2006 to 2020. The forest burnt area and the number of fires were collected monthly. Climatic data, including average temperature, average relative humidity, and the average wind speed, was acquired from the station nearest the fire location using the Czech Republic Hydrometeorological Institute.
The following parameter estimations related to dynamic and stochastic properties of air temperature, relative humidity, and wind speed can be used in the firefighting capacity optimization problem. Air temperature can be considered as a sine function of time with some residuals. And here we have the PDF of the temperature residuals. Note that this function almost looks like a normal distribution. And here we have relative humidity as a function of F2. You see F2 to the right, which is a kinked linear function of time, where time is the time of the year. And you also find the residuals and the properties of them. The PDF of the relative humidity residuals looks like this, and again we almost have a normal distribution. It's even better to express relative humidity as a function of F2 and of the residual in temperature. And here we see how this works, and we see that the residual in temperature and relative humidity have strictly negative correlation. We see here that the relative humidity is negatively affected by increasing temperature residuals, which can also be expected. The PDF of the relative humidity residual looks very nice. It's almost a perfect normal distribution. The wind speed shows a very dramatic and stochastic pattern, and it's not easy to find any seasonal variation of a simple type. And here this graph represents day numbers from January 1, 2020 until December 31, 2021, so it's 2 full years. The probability distribution of wind speed looks like this. Very rarely we have 0 meters per second, and very often we have 1 meter per second. In this area, it's very uncommon to have more than 5 meters per second. Conclusions. The optimal firefighting capacity is a dynamically changing function of several parameters. The optimal solution has been derived and presented in general form. Comparative statics analysis has been used to show how the optimal decisions are affected by parameter changes. Since the optimal decisions are functions of many local cost parameters, and since different regions have different and dynamically changing weather parameters, the optimal capacity solutions are not the same in different regions. The general approach presented here should be possible to use in most countries and regions of our world. Thank you very much for your time and the most interesting conference.